This section explains the inversion that organizes the book. What is hard for people, chess, arithmetic, is trivial to program. What is effortless for people, recognizing a face, recognizing a spoken word, resists every attempt to write down as rules. Knowledge you cannot state, you cannot hand code. So the machine must acquire it from experience instead. The unit it acquires is a representation, raw pixels seen through learned features rather than given ones. Depth is the recursion. Each concept is defined by simpler concepts, a hierarchy. The system builds instead of receiving. The title names that recursion, not the network. Deep learning is the escape from the knowledge engineering bottleneck. Stop dictating what to know. This section explains the opening move of the book's first chapter and why it sets up everything that follows. The tasks a computer finds hardest are exactly the ones a human finds effortless. Recognizing a face, recognizing a spoken word. They are hard for the machine precisely because effortless knowledge is informal, unsayable, impossible to hand code as rules. Chapter 1 sets the book's whole arc against this inversion. Its answer is a single generative move. Let the machine acquire its own knowledge from data and let it build complicated concepts out of simpler ones. Stack that composition and the concept graph grows deep, many layers, which is all that the term deep learning names. The chapter walks the ladder that forces depth. Hand-coded rules fail. Hand-designed features strain. So the representation itself must be learned. Everything later in the book is machinery for that one climb. This section explains why linear algebra is the single alphabet in which deep learning is written. The linear map. The chapter's thesis is that a matrix is not a grid of numbers, but an action on space. It stretches, rotates, and collapses, and every quantity the book later optimizes lives as a point that such actions move. The generative primitive it hands you is decomposition. Factor a transformation into the directions it merely scales. The eigendirections or the orthogonal frames. It maps between the singular values and its behavior becomes readable. PCA is the closing anchor, decomposition earning its keep, compressing data onto the axes of greatest variance. Everything after inherits this. A network is linear maps composed, punctuated by non-linearity. This section installs the single object deep learning needs. Deep learning runs on continuous mathematics rather than discrete, and this chapter builds the one object that follows from that, the array of numbers indexed by axes. Scalar, vector, matrix, and tensor are a single object seen at rising axis count 0, 1, 2, and n. They only look like 4 separate things. Because they are one grid, every operation you meet later is some reshaping of that grid. The shift the chapter asks for is geometric, and it is the move that makes the rest of the book go through. Read a vector as a point in n-dimensional real space, and read a matrix as a map that moves such points. The table of entries is just how that map is written down. Once data is a point and computation is a transformation of space, the whole book's machinery, that a network is composed, maps, becomes predictable from here. This layer introduces the language of probability and information theory that every later chapter will speak in. Deep learning runs on deterministic hardware, yet it must reason about a world it never fully sees, noisy sensors, unobserved causes, models too coarse for the truth. probability is the single consistent algebra for that ignorance. This chapter hands you its vocabulary, random variables, distributions, and expectation, so that every later loss and generative model can be written in it. Information theory is the other half. Entropy measures the surprise a distribution carries. KL divergence measures how far one distribution sits from another, which is exactly what training minimizes. The chapter is scaffolding, not argument. It fixes the language in which the rest of the book states every objective, because learning, stated cleanly, is fitting a distribution to uncertainty. This section explains why probability and information theory form the mathematical foundation this chapter builds on. Every proposition a learner touches is uncertain, and this chapter's move is to show that uncertainty is not a defect to be engineered away, but a single quantity obeying an algebra. 3 sources feed it: genuine stochasticity, unobserved variables, and lossy models. All 3 collapse to one representation, a distribution. Probability then extends logic to propositions that are not simply true or false. A scalar degree of belief inherits axioms rich enough to derive new beliefs from old. Information theory supplies the duometer, how much a distribution surprises you. It quantifies the uncertainty that probability merely represents. That pairing is the chapter's purpose in the book. It hands deep learning its native tongue, since every later loss function is written in exactly this vocabulary. This section explains numerical computation, the chapter where deep learning meets the finite machine underneath the mathematics. Deep learning never solves its equations. It approaches them one finite precision step at a time, and this chapter is where the book admits the hardware beneath the math. The continuous objects, the reals, the gradients, the probabilities must survive compression into finitely many bits. The error that matters is not how wrong your model is. It is how badly arithmetic amplifies rounding. 2 forces govern that survival. The first is overflow and underflow, where a softmax exponentiates itself into infinity or into 0. The second is conditioning, meaning how violently a function magnifies a small perturbation in its input. Everything downstream, every train network, is gradient descent, step opposite the slope, then repeat. The whole discipline is iterative refinement on hardware that cannot hold a single real number. This section explains why real arithmetic on a finite machine is a lossy quantization. Infinitely many real numbers collapse onto finitely many bit patterns, and each collapse discards a little. That is the primitive of the chapter. An algorithm that is correct over the real numbers is a different object from its floating point image, and the gap between them of this floating point image and the gap between them is the error you have to budget for. 2. Failure modes, name where the map tears. Underflow, where something small collapses to 0. Overflow, where something large blows up to infinity. Both of them breed, not a number. The anchor is softmax, stabilized by subtracting the maximum of the inputs. Analytically, it is the same function. Numerically, it is a different path, routed around the torn regions. Conditioning measures how strongly the map amplifies error that is already present. The discipline that governs everything downstream, gradient descent included, is to choose the route the machine can actually represent, even when a truer route exists on paper. This section explains why the machine learning chapter is the foundation the rest of the book stands on. A learning algorithm is defined by what improves in it, not by what it computes. Performance, P on task T, rises with experience. E. This is Mitchell's definition, and it is the seed of the whole chapter. Everything the book builds rests on one split. This chapter installs. The goal is to generalize to unseen data. Fitting the training set is only the means, and the gap between fitting and generalizing is the only quantity that matters. Capacity tunes that gap. Too little capacity underfits. Too much memorizes. So learning becomes statistics done by machine. Estimate a complicated function, control the generalization error, and forget the confidence intervals. The chapter is the book's foundation stone precisely because deep learning inherits this frame unchanged. Only section 5.11 turns to why the classical version stalls, and that is what motivates everything after. This section explains what a learning algorithm actually is, and the single quantity the whole chapter asks you to watch. A learning algorithm is a triple, a task T, a performance measure, P, and an experience E. Its skill at T, as scored by P, improves as E accumulates. This is Mitchell's definition, and it reframes learning as something that gets better with exposure rather than a fixed piece of code that solves the task. The chapter carries one thesis. The quantity worth watching is never the training error, but the gap between that error and performance on unseen data. Generalization is the whole game. Capacity, regularization, the bias variance trade, and the choice between frequentist and Bayesian estimation are all bookkeeping over that one gap. Everything the rest of the book does is a move on the same board. The closing turn in section 5.11 plants the seed for what follows. Classical methods generalize badly as the dimension climbs, an effect named the curse of dimensionality, paired with the no free lunch theorem. That wall is precisely the one deep learning is built to scale. This section explains why a deep, feed-forward network is the generative seed of every architecture that follows, starting from the one problem a linear model cannot solve. A linear model sees only what its fixed features let it see. The XOR problem defeats it because no straight cut separates the two classes. Stack, an affine map, bend the space with a nonlinearity, then apply another affine map, and the once tangled points fall on either side of a line. That is the whole primitive. A feed-forward network is a chain of simple maps whose composition learns the representation a linear model had to be handed. The depth is the composition. The training is the choosing of the bends. Every later architecture, convolutional and recurrent alike, specializes this same template, so the chapter is the book's generative seed from which every other model grows. The features stop being input and become output. This part explains what a feed-forward network is at its core. A feed-forward network is a function approximator. It fixes a compositional shape. The function f is f3 composed with f2, composed with f1, a directed acyclic chain, and it searches for parameters theta that bend f of x given theta toward an unknown target f star. The generative move is that supervision touches only the endpoints. The training data pins what the output layer must emit, never what the intermediate layer should compute. Hence the word hidden. The layers are the unconstrained interior. The learner must invent to make the endpoints consistent. Depth is just the length of that chain. Width is the dimension of each vector-valued stage. Everything downstream, the activations, the gradients, the architecture, is elaboration of this one primitive, composition under endpoint. This section explains why every regularizer in deep learning is a prior, a preference declared before the data speaks. The chapter carries a single thesis. Generalization error falls not by fitting the training set better, but by deliberately restricting which functions the optimizer may reach, spending a little training error to buy back variance. Goodfellow states it flatly. Any modification intended to reduce generalization error, but not training error. The bias and variance trade is the whole engine, and every technique is one move seen from a different angle. You can constrain the hypothesis family as weight decay does. You can inject invariances you already know through augmentation and noise. Or you can average many hypotheses through ensembles and dropout. Each of these encodes knowledge that the data alone can drop out. Deep models run over-parameterized, so the question is never whether to prefer, only what to prefer. This section explains regularization as a single primitive that runs through the whole chapter. Regularization is any modification that trades increased bias for reduced variance, profitable exactly when variance falls more than bias rises. That is the whole primitive. Every technique in the chapter is one instance of it. The reframing that makes it generative is this. You are always fitting a square peg into a round hole. The square peg is the true data-generating process. For images or text, essentially the whole universe. The round hole is your model family, which the true process almost never inhabits. So the intuitive goal, finding the right-sized model, is the wrong target. The winning move inverts it. Build a model too large, then regularize it back from the overfitting regime into the matched one. This depends on the bias variance decomposition from Chapter 5. This section explains why training a deep network is optimization that works against its own stated goal. Training a deep network is optimization that refuses its own goal. What you can actually descend, the average loss on the training set, is a proxy for a proxy. Empirical risk stands in for the true risk over the data-generating distribution, and a differentiable surrogate, the negative log likelihood, stands in for the loss you actually care about, the 0-1 error, which you cannot differentiate. So the quantity minimized is 3 times removed from the quantity wanted. Convergence to its minimum is a failure. You stop early, before the proxy and the target diverge. This is the chapter's hinge. Every algorithm that follows bends toward generalization, not toward the bottom of J. Descent is the mechanism. Not quite descending is the point. This section explains why training a neural network is an optimization that never touches its own target. You care about the generalization error under the true distribution, and that quantity is unmeasurable, so you descend a training set average instead. That average has no usable gradient for what you actually want, the 0-1 loss, so you descend a differentiable surrogate, and you halt before reaching any minimum, stopping at the moment a held-out signal says, overfitting any minimum, stopping at the moment a held-out signal says overfitting has begun. Each of these moves swaps the true objective for a tractable proxy, then hopes the proxy drags the real quantity along with it. The whole chapter is the discipline of that indirection. The contrast with pure optimization is sharp. Pure optimization minimizes the cost function, J, because J is the goal itself. Here, J is only ever a lever on something you cannot see. This section explains what a convolutional layer really is at the structural level. A convolutional layer is a fully connected layer with an infinitely strong prior wired into its weights before any data arrives. Most connections are forced to zero, and the survivors are forced equal across every position. That single move, zero the distant weights and tie the rest, is the whole chapter. It buys three things at once. First, sparse interactions. Each output sees a small patch, not the whole input. Second, parameter sharing. One kernel reused everywhere. Third, equivariance to translation. Shift the input and the output shifts identically. The generative primitive is this. An architecture is a prior. Instead of hoping a general network learns that vision is local and position agnostic, you carve that belief into the connectivity. Convolution is just constrained. Matrix multiplication. This part explains the convolutional network as a single structural substitution. A convolutional network is an ordinary neural net with one substitution. In at least one layer, general matrix multiplication becomes convolution, the same small kernel slid across the input rather than a free weight for every input-output pair. The generative primitive is symmetry as constraint. When the data carries a known grid topology, time as a one-dimensional lattice, or an image as two-dimensional pixels, translation invariance is built into the linear operator instead of learned. That forces the weights to be shared and local. Everything the chapter builds, pooling, strides, and multi-channel variants, elaborates that one move. What it deliberately withholds is which architecture to assemble from these blocks. The chapter hands you the operator algebra, not the recipe. This section explains the structural primitive behind the whole chapter on sequence modeling. A single function applied to itself, once per time step, is the entire idea. Recurrence shares one parameter set across every position of a sequence, so the same function f, taking the previous state, ht-1, and the current input xt, maps the state forward, whether the input xt maps the state forward, whether the input has 5 tokens or 5,000. Unfolding that recurrence into a computational graph turns a fixed size transition into arbitrary depth. The network size decouples from the sequence's length. This is the temporal twin of convolution's spatial weight sharing. The book places both under one principle, statistical strength shared across a structured index. Everything downstream is elaboration of what this one shared transition can and cannot carry across distance. That includes teacher forcing, the bidirectional and encoder-decoder variance, and the vanishing gradient problem that motivates gated memory. This section explains the single idea behind recurrent networks, one function applied to itself. A recurrent net is a dynamical system unfolded. The state at step t equals f of the previous state and the parameters theta. The same f, the same theta at every step of a chain as long as the sequence. That single reuse transition is the entire idea parameter sharing across time. It buys what a fixed width feed-forward net cannot. It generalizes to lengths never seen in training, and it is position invariant, so the token 2009 is caught whether it lands as the 6th word or the 2nd. A convolution shares one kernel across space. Recurrence shares one update, rule across depth, folding an arbitrarily deep computation into a constant parameter count. This is the chapter's place in the arc. The sequence-specialized architecture stands to time as the convolutional net stands to the grid. This section explains what the practical methodology chapter contributes to the rest of the book. Everything else in the book is a catalogue of models. This chapter is the controller that decides which one to reach for and when. The generative primitive is that an applied learning system runs as a feedback loop rather than a menu you pick from. You fix a target error metric, you stand up an end-to-end pipeline immediately, and then you let instrumentation tell you what to change next instead of guessing. The surprise the authors lead with is that correct application of a commonplace algorithm beats sloppy application of an obscure one. Expertise here is the diagnostic discipline of attributing a performance gap to its cause, whether that is underfitting, overfitting, bad data, or a software defect, before touching anything. It is that discipline rather than breadth of technique. This section explains why deep learning competence is best understood as a closed-loop control problem. The chapter's whole claim is that competence here is a matter of feedback, a control loop, rather than a catalog of algorithms. You win by applying a commonplace method correctly, rather than an exotic one, sloppily. The generative primitive is a short cycle. Fix an error metric and a target. Stand up an end-to-end baseline immediately, then instrument the system to localize the fault. Is this loss overfitting, underfitting, bad data, or a software defect? And make one incremental change per diagnosis. Blind guessing is open loop. This is feedback. Everything downstream, which baseline to pick, when to gather data, how to tune, is just the actuator that the diagnosis selects. The expert is the one whose measurement tells them where to push, not the one who knows the most models. This section explains what the applications chapter adds, once the earlier chapters have specified what a network computes. Everything before this chapter tells you what the computation is. This one is about making that computation survive contact with real scale and real domains. The invariant move is to exploit structure to defeat cost. A vocabulary too large to normalize over becomes a tree through hierarchical softmax and importance sampling, so the partition function stops dominating. Hardware too slow becomes mixed precision arithmetic, split across data and model parallelism. Vision, speech, and language each reuse the same learning machinery from part 2. What differs is only which bottleneck a domain forces you to make cheap: output cardinality, latency, sequence length. Applications adds no new theory. It is the engineering discipline of fitting one invariant algorithm to each domain's particular scaling wall. This section explains why the practical art of deep learning is a story about scale before it is a story about algorithms. Competence belongs to the population, not to the unit. That is connectionism's wager, and this chapter is its engineering consequence. No single neuron is intelligent. Enough of them, coupled together. So the practical art of applying deep learning is the art of making the network large, which turns applications into a hardware story, GPUs, and distributed training before it becomes an algorithm story. There is a residue, the author understates. Generality has not arrived, so scale still pays a specialization tax. Each domain enters through its own bottleneck, vision drowning in pixels per example, language drowning in vocabulary per feature. Read the chapter as one claim. Intelligence is emergent with size. Everything downstream, the silicon, the parallelism, the per-domain contortions, is the cost of buying that size. This section explains why the classical linear factor models are all one template. One generative recipe subsumes the whole classical zoo, draw latent factors h from a prior, push them through a linear map where x equals w times h plus b, then add noise. Factor analysis, probabilistic PCA, independent component analysis, sparse coding, and slow feature analysis differ only in the prior placed on H, whether Gaussian and slow feature analysis differ only in the prior placed above a, Weyl W, known Gaussian, sparse, or slowly vary. The chapter's role in the book's arc is scaffolding. It strips generative modeling down to its minimal linear core so that the later deep, nonlinear generators read as loosening one assumption at a time. The predictive payoff is this. Choose a prior, and you recover a named method. The decoder stays linear, so all of the representational power lives in what structure you impose on the factors, not in the map. This section explains why linear factor models open the generative model's arc. Strip away every sophistication and a generative model is just a decoder. You sample hidden factors, push them through a map, and call the output data. Linear factor models are that skeleton at its barest. You draw independent factors h from a prior p of h, then set x equal to w times h plus b, plus noise. The whole chapter's payload is that one equation. Probabilistic, PCA, factor analysis, and independent component analysis are a single template differing only in two knobs, the shape of the noise and the prior on H. That is why they open the generative model's arc. Every degenerative model downstream keeps the sample then decode move and nearly swaps the linear decoder for a nonlinear one. The linearity is the training wheel. The generative idea itself is sample, then decode. This part explains what an autoencoder is at its most structural level. Force a network to copy its input to its output, but route the copy through a channel too narrow to carry everything. Now, perfect copying is impossible, and the model must spend scarce capacity on whatever structure is most worth keeping. That constraint is the entire teacher. The reconstruction target is a pretext. An autoencoder is the identity map denied enough room to be the identity. The encoder learns which coordinates matter, and the decoder rebuilds from them. A bottleneck, which is called undercompleteness, or a penalty, such as sparsity, denoising, or contraction, supplies the denial. Either way, the useful representation falls out as a byproduct of a copying task. The model is engineered to fail gracefully. Learning to reconstruct badly in the right way is learning to represent. This section explains the autoencoder and the single primitive that makes it work. An autoencoder learns the identity map, but the whole design fights that success. Copy the input to the output perfectly, and you have learned nothing. The useful thing appears only in what the network is forbidden to reproduce. Squeeze the code below the input's dimension, or penalize it, and the reconstruction loss becomes a selection pressure. The model must spend its scarce capacity on the input's most salient structure. The output is discarded. The internal code H is the product. That single move is the primitive. Impose a constraint, then harvest the representation it forces. Under completeness, recovering the subspace of principal component analysis is just its linear shadow. Everything downstream, sparsity, denoising, contraction, is a different constraint plugged into the same frame. This part explains what representation learning is, and why the form of the data, rather than the data itself, is what makes a task easy. Divide the Roman numeral CCX by the Roman numeral VX, and the first thing you do is convert to Arabic numerals. The representation is what makes the task tractable, not the quantity. The same point shows up in data structures. Inserting an element is order n on a linked list, but order log n on a red-black tree. Same operation, same content, different N1. Representation learning takes that principle as its objective. Rather than engineering features by hand, you learn the encoding under which the downstream task becomes easy. A supervised network already does this implicitly. Each hidden layer reshapes the input until a final linear classifier can separate it. The chapter's move is to make that encoding the product itself, learnable without labels. One representation then carries statistical strength across many tasks, unsupervised structure feeding supervised prediction, knowledge transferring to places where labeled examples are scarce.